Yes. Please.
Click the OK button and dive in. So Leo, thank you very much. Appreciate the gentle introduction, so to speak. And indeed, I think everything I'm going to talk, almost everything, not quite true, almost everything is going to be inspired by additive manufacturing. But I actually will start off with talking about some results on conventional titanium, and of course it's going to be all titanium 6 aluminum for vanadium. You can see that a lot of people have contributed to this. Nearly all of what I'm going to tell you has actually been published or almost published, so I'm not particularly worried about people making notes. And so the two pictures that you see, this rather strange looking object here is a part, and you see the dimensions. It's Ti-6-4. It's been deposited by wire directed energy deposition, specifically a laser hot wire system. And even in this very low magnification optical set of images, you can see the vague outline of the beta grain structure. You can also see the scalloped edges, so each scallop is one bead that's been deposited. And you can also see a feature here that we call white bands. And so you see these horizontal, they're almost horizontal lines, very close to horizontal lines. But if you look really carefully, you'll realize that those white bands don't actually line up with the weld beads. So they are a microstructural feature that depends on the local thermal history. And the picture on the right actually is a depiction of the fraction of colony microstructure. I'll try and remember to explain that a little bit later on, but basically where the alpha beta lath is very well aligned. Basically you have only one variant of the alpha. And we claim that the calculated white band structure corresponds well to the actual white band structure. And I will give you the rest of the story in just a moment when I get to that slide. So let's plunge in. Oops, and first I've got to find the right arrow key. There we go. So I have an agenda, so to speak. And there are enough topics on this that I'm not going to explain. I'm just going to, at high level, I'm going to talk about R values, otherwise known as Langford coefficients. I'm going to talk quite a bit about high-speed diffraction experiments because that's the kernel, if you like, of the scientific content here. But I will come back to the question of what do you do with Ti-6-4 once you printed it? And the answer to that is if you're going to use it for real parts, you have to qualify the process. And qualification of a manufacturing process is something it's something a little bit beyond what materials people typically deal with. And I'll say for myself that it's only in recent years that I've had any idea what qualification and certification are all about. But the other way to say it is that if you're dealing with parts that go into the aerospace business, you have to worry, very often you have to worry about fatigue. And the question then becomes, well, can you predict the fatigue based on what you know about the manufacturing? And so we are attempting to build a digital twin that does that job, that takes what we know about the process and predicts the fatigue life. So that's going to be very high level and quick, but I just want to give you some idea of what's going on. Okay, so I need to keep moving if I'm going to be get through this in a reasonable time. So titanium with 6% of aluminum and 4% of vanadium is an alloy that's typically used in a mixed phase state. It has roughly 90% alpha, depending on its history, and the remainder is beta. the aluminum stabilizes the hexagonal phase, and the vanadium stabilizes the body center cubic phase. And as nearly everybody on this call is, I'm sure, quite well aware, when you freeze titanium, or Ti-64 as I'm going to call it, then what you first get is the beta high temperature phase, and then it undergoes a solid state phase transformation in the vicinity of 1000 centigrade. Now that phase transformation, if you cool slowly, you get a diffusional transformation. The aluminum goes into the alpha and the vanadium goes into the beta, and you get a mixture of alpha and beta. And if you give it enough time, then you get something close to the equilibrium amount. However, if you cool it quickly enough, then this particular alloy can undergo a martensitic, in other words, a diffusionless or military type transformation. And so that can only occur if you get below the so-called T0 line, in other words, where the transformation can occur without any diffusion, without any change in local composition. And so what we find is that under high cooling rate conditions, such as you find in laser powder bed fusion, you do actually get alpha prime, in other words, the martensitic form. But it can and does decompose to alpha plus beta when you reheat it. In other words, when you heat treat or you apply hot isostatic pressing. And I'm actually going to address both of those issues because they are interesting. And it does matter a lot to the strength, to fracture toughness, to fatigue, which of these microstructures that you get. So, and then the other issue with this alloy is the beta has a grain structure. And so particularly under slow cooling, then the phase transformation can initiate, heterogeneously, of course, on the prior beta grain boundaries. So that gives you grain boundary nucleated alpha. And I'm going to make a very brief discussion about macro zones, which is really grain boundary alpha of a particular orientation, and mainly how that motivates the need for quite large scale EBSD. And that's a comment about, sort of the trend to apply EBSD to everything. It's great, wonderful technique, but what I find with my students is that they get obsessed by what they can see, and EBSD maps tend to be much too small compared to the original grain size in the beta. So that was a bit of a sort of tutorial remark. Okay, so as with any transformation, you can develop either time temperature transformation diagrams or continuous cooling diagrams. And so what you see in the top right is such a diagram for Ti-64. The idea, one of the key ideas here is that the diffusional transformation, which is pretty classical in terms of its kinetics, can either start at the grain boundaries or it can happen in the bulk. And the two sets of curves are shifted to higher temperatures because the nucleation barrier is so much lower. And so if you want to model what microstructure to expect from this solid state phase transformation, you have to account for all of these possibilities. And you also have to account not just for the alpha beta lath, but for the possibility that you're going to get this so-called colony structure where basically you selected only one variant. And so we have published something on this. That was this model that we developed is essentially a multi-phase Kolmogorov-Johnson-Mailavrami model, KJMA. And so each part of that obeys the standard equation. But of course, it gets a lot more complicated when you've got multiple phases. So there are a lot of assumptions that you have to make. You have to be careful with your martensite model to make sure that it's composition dependent, just as in steels. but that was the basis for those white bands. And so remembering to explain the white bands, the way that comes about is if you reheat the material, which always happens or almost always happens in additive manufacturing, and you take the material up to the very top of the alpha beta range, but not quite high enough to completely turn it back into beta, then you can get rapid coarsening of that last structure such that you end up with colony structure. And if you get a colony structure with a roughly 1 micron last spacing, that's very closely analogous to pearlitic structures in steel. And so under optical microscopy, you get this characteristic difference in the appearance. So I'm not going to be able to say anything more about it, but that at least gives you some idea of where that goes. Okay, so the bottom line up front, as it were, in terms of microstructure in Ti-6.4 is that cooling rate is important. I'm going to explain it. You get strongly epitaxial growth in the beta, and it coarsens. And so what you probably didn't notice right away is that as you build up basically in any of these additive processes, the beta grain structure gets coarser and coarser and coarser. So even if you started with a reasonably fine grain structure, it coarsens dramatically, and you can easily have 200 micron width grains, 300 microns. When it goes through the phase transformation, if that happens slowly enough, you get a nice, well-developed last structure. You see an example of that in the top right. That's what you typically get with wire deposition. However, if you do laser powder bed fusion and you don't take the material up to a high temperature afterwards, then you do get a martensitic structure. It's not necessarily pure, so to speak, martensite. In fact, this micrograph has hints of the beginnings of tempering or decomposition. So I'll tell you a little bit about that. So it means that the microstructure that you get, even as printed, is quite sensitive to local conditions. Although if you deliberately heat treat and you go hot enough, high enough in temperature to decompose the martensite, you can, to some extent, regularize the microstructure. So before I get into that, one of the very nice things that happened in the last couple of years was I had the opportunity, thanks to the Franke Foundation in Belgium, to spend a substantial amount of time with Leo in Ghent. And one of the things that we worked on was trying to understand the anisotropy in regular Ti-6.4, regular conventionally produced. And this was the thesis work of somebody called Luca Corallo, the first name in this paper on the bottom here, who was a student with Patricia Verleysen. And amongst other things, what he did was tensile tests and measuring the strain ratio. So this was interesting because there's a substantial literature on deep drawing steels and a lot of modeling of the problem, and a well-developed correlation between the strain ratio, or R value, and drawability. So it's a known aspect of texture that's very useful in the formability world. But Ti-6.4 has been mostly used for bulk parts and not so very much in sheet form, certainly, and not a lot of deep drawing of Ti-6.4 sheet. So this work was kind of groundbreaking in that they did these tensile tests in lots of different directions, and they did this at both quasi-static and dynamic strain rates. Now, I have this remark about R value being a really sensitive probe of anisotropy. So what you see here are some pole figures, actually simulations of rolling, plane strain compression in FCC metals. And these things down below here with all of the lines are depictions of yield surfaces. And I realize that a yield surface is a rather specialized topic. But for those of you that have seen a yield surface, this is actually a pi-plane yield surface. And when you have a strong texture, you get really quite sharp corners in this yield stress. So what does a corner mean? A corner means that if you stress the material and you go out in this direction, then the strain rate that you get from that is perpendicular, normal to the edge of that yield surface, the yield line, or the yield locus. So if you look at this corner here, you get a very different strain rate, straining direction in this direction than if you load it in this direction. So the R value is actually measuring that slope of the yield surface. And if you have an anisotropic material, then it has these corners and the R values vary a lot. So this slide is taken from some of my notes, but the point here is that there's this issue of earring when you deep draw, and both the extent and the symmetry, if you like, of the earring is very well correlated with the R values that you can measure. And when I say correlation, it's not just a data correlation. This is no machine learned model. You can actually calculate this knowing the texture. So Luca had this, worked with this conventionally produced Ti64 sheet. Those of you that know Ti64 will understand that the texture can actually vary quite a bit as a function of its history. Nevertheless, this shows you the textures. And if you deform at low strain rates, that's this pair of pole figures, in two different directions, then the texture changes, and that texture change is somewhat dependent on the strain rate. So when it says high, we're talking about 1,000 per second. When we say, where you see low, we mean more like 10 to the minus 3. So there's a mild difference in texture, but here's the real meat of this story, which is these points are the R values that Luca measured. And you notice that there are 3 different strain rates. Sorry, I said 10 to the minus 4. I should have said something a little under 10 to the minus 4, the blue points. If you test at half per second, those are the sort of ochre colored points, but pretty similar to what you see at the slow strain rate. But if you test at very high rate, 1,000 per second, then you get this, they're somewhat similar going out to 45 degrees, and then completely different, really, really different at high angles. So the challenge was, could we model this? So again, thanks to Luca and his colleagues for the EBSD data. So we used a very standard model, viscoplastic self-consistent. It's a very convenient model. And in the usual way, you're going to have to trust me if you're not familiar with it. It relies on, for input, on a list of orientations, and then it models what happens to each grain. This particular approach allows for interaction between the grains, but only via the medium. There are, of course, much more detailed models that you can run, and one could, based on the EBSD. You could run finite element with crystal plasticity. You could run the FFT code that some of you know. But it's interesting and worthwhile to see if one can get close enough with this grain-based approach. And Carlos and Ricardo have published a nice book that you can read all of the detail about how the model, the mathematical basis and how to work with it. But I've highlighted the 4 parameters associated with basic Voce hardening. And in fact, we only allowed ourselves 3 of those. We didn't use tau 1, but key difference, we did allow the latent hardening parameters to vary. So again, let me show you the R values at low strain rates on the left, those are the blue points, and the R values at high strain rate, those are the black points. But now you see some additional points. So these orange colored points on the left are the results, the best results, of course, from the VPSE simulations. And the green points on the right are the best fit that we got for the high strain rate. And you notice that it's at the high strain rate, it's pretty good, but there is still a significant deviation for 90 degrees. So at this point in time, we don't pretend to understand that or have a good explanation for it, but the general fit is quite good. Now, I'd mentioned latent hardening coefficients. I will show you the numbers in just a moment. Why would we bring that in? Well, even at low strain rate, what we found was that if we didn't allow those coefficients to vary, we got a result like these green points, and we couldn't do a good job. The other thing that needs to be said is that Ti64 is a material that it can twin, but unlike pure titanium, twinning is not a high volume fraction, and it was not observed in this material. So we felt like we had to try to explain this just based on slip. So now you see the actual numbers. I know this is a horrible thing to do to an audience, to ask them to read a whole lot of numbers, but tau 0, tau 1, sorry, when I said we use 3, we're using tau 0, tau 1, those are two, that's the initial CRSS value and the large strain value. Theta 0 is the initial hardening rate, and theta 1 is the asymptotic, but that was set to 0, just based on fitting stress strain curves. There is no difference in the CRSS values between low strain rate and high strain rate. There are one or two of the hardening coefficients, such as here, 0.1 and here 15, that allowed us to get a good fit to the low strain rate. And then I've put boxes around to highlight that many of these coefficients changed. Actually, not all of them, but a substantial fraction of them. And that turned out to be necessary in order to get as good a fit as I've shown you. And again, I'll emphasize that there was no twinning needed to do this. Okay, that's most of the story. Let me skip over the slip activities and just point out where the CRSS values that we obtained, how they compare to the literature. And I don't think I've seen anybody do this before, but to first order, we ended up with a lower value for basal slip. Prismatic was the reference. So these are all ratios against prismatic. So basal was a bit low compared to the literature. Pyramidal A was pretty close to other values. The pyramidal C plus A was a bit on the low side, but not tremendously far away from the median. That would take too long to explain the negative version of C plus A. And then there are these 3 outlier points. So this is just to reassure you that the CRSS values were not wildly different from the literature. Okay, I'll pause and just ask if anybody has a question about this, because that was pretty quick.
Is there a question at this point about this part of the presentation?
Okay, maybe they'll think of something later.
Thank you. Please carry on.
Yep, of course. All right, so now I'm going to talk about high-speed X-ray diffraction. So what I mean by high speed is that we've been lucky enough to get a good amount of time to do experiments at a synchrotron. The synchrotron that we've typically gone to is the Advanced Photon Source in Chicago, or near Chicago. And so I think I have more details on the following slide, but the idea is you have a beam of very well monochromated X-rays. The energies are typically 50 kiloelectron volts. And we use these X-rays with an apparatus that has a fiber laser so that we can mimic the metal melting that happens in, say, laser powder bed fusion. So we have a small plate, thin plate as the sample. The laser light comes down and melts the top surface. And we typically shine the X-rays through the melt pool and arrange for the material to be fully melted where the X-rays are going through, at least on a transient basis. And you can see some of the numbers, but the dimensions are definitely the correct dimensions. And then we have a detector that can capture diffraction patterns at a rate of 250 hertz, and we get full circle diffraction patterns. So it's wide angle scattering. We also do visualization, but I definitely don't have time to talk about that. And so what do we get out of this? So the sort of diffraction pattern that you get looks like these two examples here. If you're wondering about the black lines, those are the blank spots in between the individual subpanels on the detector, but that means that we only miss a very small fraction of the area. You can see that we capture full rings out to reasonably high order. That, of course, depends on the spacing, the setback of the detector from the sample. And what we commonly do is to collapse those rings onto points, or a line, if you like. So these sort of streak camera-like plots, time starts at the bottom, marches up. The 2 theta values you see written, because of the high energy, the 2 theta values are quite small, and each line represents an individual reflection, which you can see indexed. You can see what the material looked like before melting. This sort of streak here is where it was fully liquid. Then you get the beta phase. The lines are curved because the lattice is contracting very quickly as you cool down from the melting point around 1600 down to the solid state phase transformation. In this case, you can see that the switch from beta to alpha was more or less at a given point in time. Whereas at this lower strain rate, the liquid lasts longer, quite a few milliseconds longer. You see the beta, and then there's distinct overlap between the alpha and the beta. And the resulting microstructure, while it looks martensitic, is not fully martensitic. It's worth saying that one of the advantages is that you can detect the beta to much smaller volume fractions. But in this particular pair of experiments, at the lower rate, we could detect beta after the solid state phase transformation, whereas the experiment done at high rate, the beta was not detectable, and indeed we didn't see beta in the TEM afterwards. And if you do make beta, then you can generally find it pretty easily because of the strong microsegregation of vanadium into the beta. Let me keep going. Just checking the microstructure. This picture on the left, high mag, low mag, shows a fully martensitic structure for the higher cooling rate, which is about 5,000 degrees per second. Whereas on the right, you see the result of the lower cooling rate. And you might think it's the same microstructure. Sorry, this is the fusion zone on top. This is the original material below. But there are actually small amounts of beta in between the alpha prime. So another way to look at this is to look at the unit cell volume as a sort of condensed version of the information. In the case of the higher rate experiment on the left, there is some overlap of the beta and the alpha, but the beta definitely goes away completely. Whereas at the lower rate, the transformation is slower, no surprise, but the beta persists throughout the experiment. There's still some left, even after all the alpha has formed. And there's a more obvious change in the unit cell volume between the two phases. Here there's good overlap, here there is not. So our conclusion was you need the cooling rate to be well above 1,000 degrees per second, which is very different from the literature that says you only need a few hundred degrees per second. So that was interesting. And then the other thing I'm going to show you is an experiment where we deliberately made some fully martensitic microstructure through printing at suitable conditions. And then what Sing-Yeo did was to take pieces of this and use the laser to reheat it. So no melting in this case, just taking it up to some higher temperature with these conditions and observe what happens. So all of the peaks on the way up are peaks that belong only to the alpha prime. Once you get to a high enough temperature, and I'll come back to that in a moment, what you see is that you see a phase transformation. And you first see the 110, and then you see the 200, and they, at a particular point in time, aka temperature, the beta appears very strongly. The alpha, of course, is still there, but the alpha prime peaks do interesting things. It's not just the peak area that changes, but this FWHM is full width half max. And what's quite curious is that the circles are the intensity left-hand scale, and the triangles are the full width half max. So the peaks are broadening as you go up in temperature. You expect that from thermal vibration, but they suddenly drop. They suddenly get much narrower as the phase transformation starts to happen. And so there are a number of interesting things going on here. So I mentioned temperature. So these lines over here, the ratio of alpha prime to alpha peaks. So the alpha prime goes down, of course. The numbers here in the middle one are the full width half max values. And like I said, the peaks are narrowing as you go through the phase transformation. And then when you look at the C/A ratio, then there's some interesting things happening with that, in that the C/A ratio of the alpha is measurably higher than it is in the alpha prime. So if you look at the numbers, it's changing by a fraction of a percent, but that is in fact a consistent change, and people have tried to use that to tell the difference. So what's also interesting is you can track the decomposition of the alpha prime to form alpha plus beta just by looking at the C/A ratio in the hexagonal phase or phases. All right, and then this is collecting changes in lattice parameter and in C/A ratio. So C/A ratio are the crosses, and then the circles have to do with the changes in these particular peaks. So the peaks shifting to larger values, and the change in the C/A ratio comes from the difference between the C spacing and the A spacing, of course. So you can see that in the divergence of the red curve. But you can also see how the peak widths go down and then they go back up. So what our speculation, and that's all it is that you're forming some kind of an intermediary phase. So if you're curious, you can look that up in this paper. All right, so some lessons learned, just to summarize quickly. You only get the fully martensitic beta to alpha prime, sorry, left off the prime, only at cooling rates on the order of several thousand degrees per second, at least an order of magnitude above what you see in the literature. It's comfortably explains why we see martensitic structures in laser powder bed fusion, but not in electron beam, which typically uses much larger preheats, or for that matter, in wire deposition, which is more like a welding process, much larger weld beads, much slower cooling rates. And these remarks are backed up by some of these high-speed synchrotron experiments that we've done. Something that represents future work, this penultimate bullet, is that the microstructure prediction code that I mentioned at the beginning doesn't yet have a good model for what I'm calling the tempering of Ti-6-4, in other words, the reheating, but that will definitely be needed. And then there are lots of other applications. All right, so for a few minutes, I will explain why large area EBSD is not only necessary, but actually pretty interesting. This slide summarizes a lot of the aspects of the laser hot wire project that we were involved in. The laser is much bigger than you find in laser powder bed. It was a 6 kilowatt laser. So you can deposit a lot of metal, and there's a lot to say about process control. Oh, I should play this little movie for you so you can see what's going on. You can develop diagrams that tell you how to optimize the process, and so all of this is available. But what I want to highlight is we worked with Jake Benzing at the Boulder office of NIST, and he very kindly did some large-scale EBSD for us. So on the left, you see one of the single bead walls, and you can see representations with IPF color of what was actually measured, in other words, the alpha. But as a lot of you know, what's now readily available in various packages is you can take the martensitic structures and you can use them to back calculate what the parent phase orientation was, the beta phase. And so you can see a roughly equiax structure at the bottom of the bead, coarsening happening rapidly. And then at the top of the bead, there's one dominant beta grain and a few other grains in there. So that's some evidence for that rapid coarsening that I mentioned. I'm going to skip over this for lack of time, but should be no surprise that the strong beta texture gives rise to significant anisotropy. And again, we use VPSC to try to model this. But the particular aspect I'll spend a couple of minutes on that is published and available is, and this is the work of Rajiv Halder in my group and Sahu in a group in India. And what we did with those maps was to do some more maps. So on the left was a single bead, like what I've shown you. On the right, what you see is a multi-bead wall. So in other words, depositing several tracks next to each other with enough overlap to form a monolithic piece. And so when we looked at the microstructure in a bit more detail and paid particular attention to the grain boundary alpha, even in the image quality map, you can see these sort of white streaks at certain of the boundaries between the beta grains. And so where you see a white streak on the left, you see a black line developed where we identified macrozones. Now, defining what a macrozone is would take more detail than I have time for, but it's where you have a significant amount of grain boundary alpha, and that alpha is well aligned across the grain boundary, which makes it a site where slip can easily start. But the thing that was really interesting is there are grain boundaries in the beta in the single bead walls, and there are grain boundaries in the multi-bead walls. The beta grains grow up through these weld boundaries. That's very easily, as you can see from the strongly columnar microstructure. But what was quite interesting was when we quantified the length fractions of macrozones. In other words, what length fraction of these beta grain boundaries had these special orientation relationships. The answer turned out to be that the multi-walls had quite a lot more, measurably more of these macrozones than the single wall. So We're not claiming that we fully understand how this is happening. There is maybe best to say just some speculation that it relates to the different thermal histories and different thermal stresses. But it is, I think, a pretty strong argument for the value in doing large area EBSD as well as the fine scale work. Okay, so I'm going to finish by talking about fatigue. And again, it's going to be quite high level just to give you some idea what's going on. We had a large NASA-supported project where we printed lots and lots of these 4-point bend fatigue bars. So you can see the individual bars still sitting on the plate. We did computed tomography on a pretty good fraction of them. And then we applied 4-point bend fatigue, which turned out to be a very useful way to do relatively high throughput fatigue testing. Maybe not the ultimate in throughput, but not too bad. And what that allowed us to get were lots and lots of individual points. And so what you see here, the bigger diagram, is an SN curve type of plot, alternating stress on the vertical axis and cycles to failure on the logarithmic horizontal axis. And then over here on the bottom left is a crude sort of process map and an indication of what process conditions we were using. And suffice it to say that the Goldilocks zone, so to speak, is somewhere in the middle in the gray. If you go too fast at the given power, you don't melt all of the metal, and we call that lack of fusion. If you go rather slowly at the same power, you get keyholing. And so the results coming out of the lack of fusion zone were terrible, meaning very short, relatively short fatigue life at low stresses, low alternating stresses. As we moved closer to the process window, the fatigue performance became a little better, not quite such low stresses. When we looked at the keyhole range, that was actually fairly similar to what we see close to the edge of the lack of fusion zone. And again, I'm talking quickly and assuming a lot about your knowledge of printing, but because of the pores being nicely spherical, they had a less bad effect on the fatigue. As you move into the process window, the fatigue performance gets quite a bit better. And then finally, right in the middle of the process window, what you get is a large range of behavior, large range of fatigue life, but these little arrows over here are pointing to cases where there was a run out. In other words, the test went all the way to 10 million cycles and failure did not occur. So remarkably enough, at a substantial fraction, if not equal to the yield stress, the sample can, under some circumstances, survive a full 10 million cycles, but sometimes very short life. So what was going on here? Well, when you plot the maximum stress at which you see a run out, those are the blue triangles, and you also plot these red diamonds, the pore density. So that's the log scale over here. What you notice is that the pore density comes down as a function of the scan speed, and then it goes back up. And the fatigue performance goes up into the process window and then comes back down. So if I add a couple of lines to guide the eye, you can see that there's a very close relationship between the defect density, which in turn is very dependent or very closely linked to the process conditions, and the fatigue performance. Well, that's a brief summary of a long topic, but what we're now doing is another bigger project where we're trying to capture everything we know about the processing and predict the fatigue. And so the way this is organized is that we have 3 major groups in the team. So we have a group that worries about the process modeling. We have a group led by my colleague Somnath Ghosh doing the multi-scale modeling and life prediction. And then we have another part of the team that is trying to use everything that we learned from the left and apply it to actual qualification and certification. And so let's take a look at what models do you need on the processing side in order to do this? Well, the answer is quite a lot of different models. You need to model the melt pool variation, for example, because that tells you the rate at which to expect defects to occur. That leads to predictions of pore distributions, but you also need to calculate what the stress concentration is, because the pore shapes vary quite a lot. If you're going to predict, as you have to do, the microstructures, then you need temperature histories. But the temperature histories themselves, the local temperature histories, depend on the macro scale temperature distribution. So this is by way of saying that there are lots of different components to this. And one of our challenges is turning out to be, hardly surprising, how to connect these models together. And so what we end up doing now is documenting and making work these many different cases of handover of data. And I think Leo's about to pull me off the stage. So just a quick summary of the microstructures. This goes back to differences between DED and laser powder bed fusion, but at least as far as Ti-64 is concerned, major differences in the general microstructure, and also lots of variations in local details, all of which are important to the objective of predicting fatigue. And then I'll let you read this and answer questions. So thank you very much for the opportunity to speak.
Thank you. Thank you. Thank you. So I'm going to stop here the recording.
Right.
So, okay.
Of course, I'm very happy to answer